As amazing as the Bohr model is, it still didn't show everything. For example, it only works for hydrogen-like atoms, atoms with a single electron. So it's either hydrogen or another atom that has lost some of its electrons, so it's an ion. It's based on an assumption that accelerating charges do not emit electromagnetic radiation if they are in specific orbits. Well, that kind of violates what Maxwell came up with, so that has to be addressed. It is excellent at predicting the frequencies of the photons that are emitted, but it does not predict their intensities. So, this is what's going to fix our troubles, the quantum model of the atom. But before we get there, there's a couple more things to talk about. The Compton effect is another phenomenon that shows that photons are truly particles. In 1923, Arthur Compton scattered X-rays off of a graphite surface and observed that the wavelength of the scattered X-rays increased. This is called the Compton shift. So we have here's a target, here's the graphite right here. We have a photon coming in, an electron pops out, that's called the scattered electron, and then we have the same, well, it's actually not the same photon. This absorbs a photon, emits another one, but that's way beyond this course. So the photon comes off at this angle here, theta, which is called the scattering angle. So what Compton postulated is that the photon, acting as a particle with an energy E equals hf, collides elastically with the electron. Now, if you'll remember elastic collisions, momentum and kinetic energy are both conserved, so the scattered photon will now have less energy as it's given up some energy to the scattered electron. So if this scattered photon right here has less energy, it will have a longer wavelength. And that's the essence of the Compton effect. In order to derive an equation to match the experimental data that showed how much the photon's wavelength is shifted, Compton had to use Einstein's equation for the relativistic energy of a particle. You don't have to worry about this. I'm just showing it here for more historical reasons. You'll see that later, where the energy is equal, energy squared is momentum squared times the speed of light squared plus the mass of the object squared times the speed of light to the fourth. So if you have a particle at rest, it will have no momentum. You will have E squared equals m squared c fourth, and that's just the famous E equals mc squared, which is the rest mass, the rest energy of a particle. Now we're going to take the case where the mass of a photon is 0. Of course, a photon has no mass, so this PC stays in. I'm sorry the x is there, but the PC stays in, and this term comes out. The m squared c fourth comes out, so you're left with E squared equals p squared c squared, or energy of a photon is momentum times the speed of light, divide through by momentum, and then you come up with that the momentum is the energy of the photon divided by the speed of light. We can substitute hf in here for E, and we can then say F is c over lambda, so we wind up with the momentum of a photon is h over lambda. This is a very key result because in the past you've heard momentum, and it is for physical objects, rocks, basketballs, etc., is mass times velocity. Here we have a massless particle, which is a photon, having a momentum. Compton then solved the conservation of energy and momentum equations, and he used the relativistic version since photons move at the speed of light, so relativity comes into play. And again, don't have to worry about that now. He came up with this equation here, which shows how much the wavelength of the scattered photon, this guy, shifts. And notice it is angular dependent. It depends on what angle this photon comes from after striking the target. So the equation is the change in the wavelength is the final wavelength, which is the wavelength of the scattered photon, minus the initial is h, Planck's constant, mass of the electron, speed of light, and theta, where theta is this scattering angle right here. With all these incredible theories and experiments and thoughts going on in the first 25 years of the 20th century, It's very interesting to note that the neutron's existence was not proven until James Chadwick demonstrated its properties in 1932. Back in 1920, Ernest Rutherford proposed that a neutral particle with a mass on the order of the proton existed so he could account for the atomic mass measurements of atoms. Before Chadwick definitively proved the neutron was there were experiments, and they actually found the neutrons, but the people doing the experiments thought that they were gamma rays or even protons. Chadwick placed a small quantity of radioactive polonium, and remember, polonium was discovered by Marie Curie, and he placed this polonium in an evacuated chamber where it decayed by emitting alpha rays, and alpha rays, of course, are just helium nuclei. These then struck a beryllium target. Neutrons were emitted from this reaction, from this collision of the alpha particles with the beryllium, and were found to have the correct mass and a neutral charge. Now, the whole point of neutrons, well, other than the fact that they exist and we're just explaining them, neutrons and protons provide the strong nuclear force that keep nuclei together. I mean, have you ever wondered how a nucleus stays together with all those positive protons, with the Coulomb force trying to repel them? Well, there's another force called the strong nuclear force that enables neutrons to attract the protons, and neutrons attract other neutrons, protons attract protons, and this balances the repulsive Coulomb force so that nuclei can exist.